Welcome. Today I wanted to spend a little bit of time giving a high-level introduction to Vault. Now, many of you, when you think about Vault, probably immediately start thinking about secret management. And that's a really important aspect, and one of the key challenges facing modern enterprises is this notion of what we call secret sprawl. It's that credentials are sprawled all over the estate. They're in plain text in Git, they're in tickets in Jira, they're in our runbook pages in Confluence, they're in our emails and our Slack messages and etc., sort of everywhere. So I think one of the key challenges when we think about trying to solve modern security posture is how do we get good at managing our secrets and have much better hygiene around them? And that's really what Vault was created to solve almost 10 years ago. So for this introduction to Vault, I want to take a step back first and really start with, well, what's the goal? What are we trying to solve for? And then from there, we'll work our way into a high-level introduction into what Vault is and how it works, and we'll kind of go a little bit deeper into Vault. But if we start with the goal, really the way I like to think about it is the outcome for most organizations that we care about is really to say, well, how do we make sure that our secrets are actually centrally managed, right? So we want to say maybe 99% of our secrets are in a vault, right? And for most of these secrets, we care about rotating them. So we want them to be rotated on some interval, let's say less than 90 days, right? So we might start with the goal, which is these two things. We want to make sure our secrets are in a vault, meaning they're access controlled, they're encrypted, we have auditing around who accessed what, and we have an ability to restrict access to people on a need-to-know basis, right? That's kind of the first part. The alternative to it not being in a vault is sort of unmanaged. It's in GitHub. Anyone who has access to that repo can see it. We don't have auditing. We don't really have strong control over it. So we kind of start with that goal, right? So if we kind of work our way backward here, the first level problem we have is when we say, well, 99% of my secrets should be in Vault, is how do I actually even know where all my secrets are, right? So the first problem we very quickly have is really a discovery problem, right? How do I know where all these secrets are? We're starting from a place of secret sprawl. They tend to be all over our estate. So the first level problem that we really solve here is with what we call Vault Radar. And the idea behind Vault Radar is how do we go discover all of these things that are already in our environment? So this includes scanning systems like Git. It might be looking for where we do our ticket management with things like Jira. It might be where we put our runbooks, so maybe Confluent. It might be where our teams collaborate, so systems like Slack, and so on and so forth, right? There's many different sources that we can connect to Vault Radar. But the idea is kind of anywhere that we work and collaborate together ends up being a place where users end up leaking credentials, right? It's easy to write a script and hard code a key, and that ends up in GitHub, right? Or I file a ticket saying I don't have access to a database, and I put the credentials that I'm trying to use, which might be in that Jira ticket now. Or I create a runbook that says, hey, here's how you go patch this thing or restart the service. And by the way, here's the SSH key to go SSH in. And so now it ends up in a runbook. So our first level challenge is how do we go discover all those things? So we can use HCP Vault Radar. We connect to all these different sources, and it scans all of them. And the reason we call it radar is it acts as an early warning radar. We want to find those credentials before an attacker finds those credentials, right? What it gives us then is an inventory of, hey, we found these 5,000 or 50,000 credentials in your environment. Those are the things we should actually move and put in a vault, right? So we can then take those secrets and import them and manage them securely by putting them into Vault. So the goal of putting them into a vault is that, we actually have a few key properties, right? One is anytime this secret is accessed, we can put an audit trail around it. So we know who accessed what secret when. More importantly, we can actually start to put things like role-based access control or attribute-based access control around it to say, okay, who needs access to that secret? Maybe your web server needs access to the database credential, but does your web server actually need root IAM permissions? Probably not, right? So how do we start to reduce the set of secrets a human user or an application or an AI agent have access to really the minimum that's kind of a need-to-know basis? That's kind of the basis when we talk about zero trust security, is really reducing access based on identity to really a need-to-know level, right? And then the third aspect of it is how are we actually storing and managing those keys? We want to make sure everything is actually encrypted at rest. As opposed to many of these other systems, which are kind of inadvertently used to store secrets, aren't really designed to store secrets. The data is not all encrypted at rest, right? They're stored in plain text, which is maybe fine for my Jira ticket, but it's not fine for my database credential or my certificates, right? So I want to make sure that everything I'm storing in Vault is fundamentally encrypted. And then lastly, that I have a centralized store for this, so that when I need to do things like rotate a database credential, I can do it in one place and do it across all of my different applications and systems, rather than have to go touch many different points and rotate and change that credential in 10, 50 different places, right? So these are all key aspects of why we want to move it to a Vault. So when we think about these first two layers, we're solving this problem. We're discovering all the different secrets in our estate, we're moving them, and we're centrally vaulting them so that we can get all of these benefits. Now, when we think about the second half of our problem statement, it's how do we keep these credentials fresh and rotated, right? If we think about moving a static secret into Vault, this tends to be a long-lived value that's shared. Meaning anytime you access that shared key value, as an example, every user is going to get the same value back. It's long-lived because it doesn't change until you manually rotate it, right? So the next level of that is really what Vault refers to as auto-rotation. So unlike a static value, this might be a value that Vault knows about. It's like a database username and password, for example, right? So with the database username and password, we might say, okay, I'm actually going to associate a policy to that says every 30 days, Vault should go automatically rotate the username and password. So in this sense, we move from a long-lived value to more of a medium-lived value, right? Now it only lives for 30 days at a time, but every user who accesses that database username and password gets the same credential back. So it's still a shared key. But the value is we move away from having to have manual rotation where we're coordinating between maybe our database administrator and our application teams to redeploy the app, to one where Vault is automatically talking to the application and talking to the database and doing that rotation in an automated way. But ultimately where we want to get to is what we refer to as a dynamic secret. These are really short-lived secrets that are created just in time so that they're unique to the client, meaning the credential doesn't exist until it's requested. The moment the user requests from Vault, I want this database credential, then Vault talks to the database, creates a new on-demand username and password, and hands that back to the user or the application. The policy can drive how long that credential is valid for. So we might say this user is only valid for 24 hours. At the end of the 24 hours, Vault will connect back to the database and actually delete that credential. So in this way, we're getting a credential that's unique to each instance that that system is being accessed, and it's very short-lived, so we don't have to worry that it gets leaked or compromised or a user leaves our organization and takes it with them. So as we get closer to dynamic, we really improve the overall security posture, right? And that's ultimately how we start tackling this rotation problem. It's impractical to have humans manually rotate thousands or tens of thousands of credentials within an organization, so we really have to move to a world where it's automated. And either we do that through auto-rotation, and we get to more medium-lived, even though they're shared credentials, or we ultimately want to get to dynamic, very short-lived, just-in-time credentials that are basically disposable. We're creating them and throwing them away on demand and using Vault to manage who has access to what and what set of credentials are active at any given time. So together, we can kind of solve both sets of these challenges and get to a much better security posture, right? So now as we think about this, ultimately, this solves really the initial focus is around machine users and applications talking to one another, right? So an app that needs to talk to another app. For example, your web server needs to talk to a database, right? In that case, the applications can automatically authenticate, fetch the credential, and talk to their systems. But we also have human users in the loop. They also need to talk to privileged systems. Maybe I'm a database developer, and I need to talk to the database to debug a query or to debug a schema layout. So how do I get the database credentials, or how do I connect to that privileged system? So Vault is designed to work closely with another product called Boundary to solve that problem. So if we think about classic user, they might need access to the database. Typically, they're going to go through a few hoops. You might jump on your corporate VPN, from which there's a firewall behind protecting it. From there, you might go through a privileged access management solution, and then from there, get to your database. So the goal is we want to simplify this with Boundary. So the idea behind Boundary is that the user will do a single sign-on using their existing identity with their existing identity provider. So this could be, Ping, Okta, Microsoft Entra, Active Directory, IBM Verify. But we use our existing identity to validate and say, great, Armon is a member of HashiCorp. He's a developer. What set of systems does he have access to? And then we can have identity-based rule that says, great, Armon's a developer. He has access to this particular database. So rather than get on the network, Boundary acts as a reverse proxy. So the user is never really on the network, and based on their identity and access, it will act as a reverse proxy to the target database. So this eliminates the need to have the user on the VPN, which means they're never on the network. And it means we don't have to manage IP rules, so we don't have to have a second layer of firewall. And we don't want to have to manage a third set of credentials somewhere. So this is where we integrate tightly with Vault. So Boundary can actually fetch the credential from Vault and use that to allow the user access to the end system, whether it's a database or SSHing into a target host. And that's where we can leverage these dynamic secrets and auto rotation. So if it's a dynamic secret, we'll fetch it from Vault, create that database username and password for that one session, allow the user to connect, and when the session is terminated, we'll delete that username and password. So we don't have to worry that the user's taking our database credential with them. Same thing if the user's SSHing into a host. We can generate a one-time key, they can SSH in, perform whatever actions they need, and when they disconnect, that key is no longer valid. There's no master SSH key that the developer has access to, right? So this starts to work in conjunction with each other to say, okay, we can solve it both for applications, machines, and AI agents in an automated way, but our human users can also come along and access those systems as well in a consistent way. So now when we start talking about the architecture of Vault, how does it actually support a whole range of different systems, right? We talked about databases, but we can also talk about certificates and SSH keys and cloud credentials, etc. So the core to Vault architecture is really the fact that it's highly pluggable, right? So the way to think about it is the Vault core is really responsible for providing a consistent API experience. So everything that you interact with Vault is really through an API, right? So whether you're coming in through the front door of maybe the UI, or you're using the CLI experience, or maybe you're even using the Terraform provider, all of those are really just clients of Vault's API, right? There's nothing special happening here. Everything goes through the front door. Everything is API driven, right? So the Vault core is really providing that API and managing to make sure that all of our data is encrypted, every operation is audited, and we're applying strong access control to these things. But now the reality is we have clients that might come from all over the place. And when I talk about a client, that might be a human user, but it also might be an application. So the first kind of point of key plugins for Vault is what we call authentication plugins, right? Or auth for short. This allows clients from different sources to prove they are who they are. So if I'm a human user like myself, I might come in through my identity provider, such as Okta, for example. So as a human user, I might come in through an IDP and verify my identity that way. But I might be an application that doesn't have an identity in an IDP, right? For example, I might be a Kubernetes application, and I would use my native service account identity to prove that I am a particular pod, for example. Now I might be a cloud native application that's using a CSP's native identity. So AWS IAM is a good example, or an Azure Managed Service Principal. So those can natively authenticate as well, and we have support for every major cloud. Now, if I'm running on-premise, I might not have that, but I maybe have an Active Directory service account associated with me. Or maybe I'm using a certificate-based method, like Spiffy or Spire as a good example, where I'm using a certificate and an identity embedded in that certificate to validate my service's identity. So there's many different plugins that Vault supports that allows applications and human users to kind of bring their identity from wherever they are, right? So we can natively integrate with all these different systems to strongly establish the identity of the end user or the end application, right? From there, we can then grant access to a set of secrets, right? So we get to the other side, which is what we refer to as secret engines, right? Think about secret engines as the various sort of pluggable integrations Vault has to different systems. So a core example of this is our key value, right? So we think about key value. That's the encrypted static secret store. So if I'm moving a static secret, it has sort of a key and a value. It's a static value. That's what key value is for. And there's a version store of this. So even if I change key values over time, I can version it and do a rollback if something goes wrong, for example, right? So that's kind of the start point. Most people start with static values and key value with Vault. But then to support all these dynamic use cases, Vault has many other secret engines. For example, we might use the PKI engine to manage certificates. This allows us to act as basically a certificate authority, or if we have an external CA, we can act as an intermediate signing authority, but we can describe different roles and then use Vault to automatically issue and rotate certificates, right? So these could be standard certificates that we're serving for internal service-to-service traffic. These could also be used for service identity. If we're using things like Spiffy and Spire, Vault could actually issue a Spiffy-compatible certificate. So it's a pretty flexible engine in terms of how we generate and manage certs. Then we could think about databases, which I've given an example of. So this could be where we actually want to integrate natively with a system like MySQL or Postgres or Oracle or DB2, where we're doing things like auto-rotation or dynamic generation of those database credentials. But this is a very long list, right? We could talk about all of the various cloud providers. We can auto-generate things like IAM keys and cloud access keys so that we don't have to have long-lived tokens. SSH is another good example where we can move away from the master SSH key and generate dynamic SSH keys that are short-lived, right? And so this list continues, right? You can think about almost any type of system that has some sort of an username and password, or has an API key, or has some sort of a mechanism that allows you to generate and rotate. Vault can have a plugin for that, so then it can manage that lifecycle of rotation and dynamic generation, right? Now, one of the more interesting use cases that's a little bit different from these is what we refer to as transit. And this is what really enables Vault to act as a little bit more than just a dynamic provider of identities or a dynamic provider of credentials, but really act as, in some sense, a trust anchor, a cryptographic anchor, by allowing you to do two things. One is define a set of encryption keys, right? So I could name these different things, right? So maybe I have, for example, a credit card encryption key, but I could also have a service authorization key, right? And then I can perform a set of operations on top of those keys, right? So an operation might be encrypting data, for example, and decrypting it. So maybe with my credit card key, I could store the actual encryption key in Vault, but then my web application might want to collect a credit card, encrypt it, get an encrypted value back, and store that in the database. So now we don't have to worry that if someone had access to the database, they have raw credit card numbers. Instead, the web app has to take the encrypted value, come back to Vault, and run the decrypt operation. And it can use Vault as basically the trusted key store to do encryption as a service. So Vault is sort of storing the keys, is acting as a key manager, but it's also offloading the cryptography, so the application doesn't have to worry about implementing encryption, decryption, signing, and verification correctly. That can all be managed by Vault. And now we can do things like key versioning and rotation. I can actually encrypt and then rotate the credit card key and have multiple versions. So I can go to version 2 and version 3, so on, right? At the same time, I can use things like, let's say, the service authorization key to generate and sign things like a signed JWT token, right? Or an OIDC token. So this allows me to treat Vault as sort of a trust anchor in a more complicated set of systems, where maybe I'm doing service-to-service authentication and authorization, but I need to have some system that has the trusted OIDC keys and the trusted JWT keys that can sign and issue and rotate these. So we have a bunch of different specific engines as well, like the JWT engine, that help automate some of these different workflows, where Vault is storing those keys, but it's acting as that sort of signing authority to enable different kind of neat workflows. So don't just think about the integrations as its only key value or its only integration to systems like databases or cloud, et cetera. It actually really turns Vault into more of a platform to enable very sophisticated security-sensitive operations, where you maybe want the keys to be stored securely in a central system and not exposed to users or applications, but you still want to enable operations over it. There's even users who store core signing keys for their crypto wallets in Vault and then enable transactions to be executed by Vault, like doing money transfers, for example, right? That's a transaction that's taking place because you need the underlying key to sign the transaction, but you don't want the key to be exposed necessarily. So this architecture really enables Vault to do a lot of very powerful things. Coming back to the basics, though, we want to make sure that every operation, whether it's coming through our UI or CLI or Terraform, is not only is it authenticated, the user's allowed to do it, there's the underlying system that's performing it, but we still want to be able to do things like audit, right? So do I actually know, well, what user performed those various operations? So audit's another key pluggable point with Vault, where we can integrate with various systems. So maybe you're sending data out to Splunk or Datadog, et cetera. So you can send out audit information to various backends. And then, of course, we want to be able to enforce policy across all of this. So Vault has a very powerful policy engine that lets us define roles, maybe by application or by users, by groups, by attributes. So it's very flexible in terms of how we want to define our different access controls and the logic around that. And the job of the core is basically to coordinate all of this. So when we configure Vault, we can enable various authentication mechanisms, we can enable various secret engines, and then we can configure where do we want audit to go and what set of policy should apply. right? So the engine itself is quite powerful and pluggable, enables us to do all these things. Now, this becomes a very key system when we think about the role of Vault. It almost becomes kind of a tier 1 in terms of availability because I have applications that are logging in, they're fetching core credentials, certificates. So if Vault is offline, that creates a problem for me. My web app can't get its database credential. It doesn't get its certificate to serve traffic. So all of a sudden we care deeply about, well, is the Vault system actually available? Is it running? Is it, can it tolerate failure? So the design of the core is also designed to manage things like data replication and automated failovers and high availability as well. So very rarely would you ever run a single Vault node. What you tend to do is run Vault in clusters. So if we think about a cluster of Vault, there's multiple nodes, right? So classic setup might be I run 3 different nodes of Vault. At any given time, one node is the leader node. That means it's coordinating the cluster, it's making sure transactions are done in a safe way, and it's replicating data to the other nodes. Now in a 3-node cluster, we can tolerate the failure of any one node, and the cluster continues functioning. If we want more availability, we can run a bigger cluster, right? So a 5-node cluster, as an example, could tolerate the failure of any 2 nodes, right? We need a majority of the cluster to maintain quorum, but effectively we can have this right size to our requirements. Now, typically as well, you run a cluster matched to your failure domain. So that might be, for example, a data center, right? So if I have multiple data centers, I can run multiple clusters. This might be in data center 1, but then I might have a separate cluster that's running in data center 2, right? And now we can enable more advanced patterns like data replication between clusters. We can do disaster recovery between multiple running configurations so that we can tolerate, if we lose a whole cluster, we can do real-time failover to a disaster recovery cluster. But the core here is not to get too detailed on the architecture. The point is that it's really designed to be a tier 1 system. So from an availability and reliability perspective, we want to be able to run things and handle the loss of a single node, the loss of an entire cluster, the loss of an entire data center, etc. We want to architect for all those different kind of scenarios. And so Vault's designed to be able to handle those kind of different configurations, right? Now, as we think about scaling this up and running it, obviously there's multiple different ways of doing it, right? So when we think about Vault's core, it really started as a software that you would download and self-manage. You could run multiple instances of it. It's effectively just a static Go binary, and we give you a Docker container of it. But in addition to that, people often want this to be managed on their behalf. It's a mission-critical system. It has complexity involved with monitoring, upgrading, etc. So it comes in a few different flavors. You can obviously self-manage Vault if you prefer to do that and want to run it yourself. But you can also use our HCP Vault service. So our HCP Vault dedicated service effectively gives you a dedicated Vault in a cloud region of your choosing. So you could pick, for example, Azure in a particular region, and we would launch a dedicated VPC with your Vault cluster running on behalf of that. And then you can do a networked link between your VPC and the managed VPC. So this gives you kind of flexibility in terms of how you want to run it in multiple different flavors. Same sort of an approach applies to Boundary. It could be self-managed, it could be cloud delivered, and then Vault Radar is delivered as an HCP service, but it has an optional component that you can self-manage and run in your own data center as well, right? So each of these is designed to come in a few different flavors to sort of solve for these different architectural requirements that you might have. Hopefully this gives a useful high-level overview when we think about the sort of challenges we're trying to solve here. It really starts at the high level of how do we discover and find all the secrets, starting from the assumption that most enterprises have a problem with secret sprawl, to really trying to move to centrally managing it, encrypting it, starting simple with static shared values, but ultimately getting into a more dynamic auto-rotated place where we can shorten the life cycle of secrets to improve our security. We have a challenge both for humans and machines. So for human users, they can access it via Boundary to really get to remote access, or they can query through the UX and CLI of Vault as well. And same thing for applications. They can be integrated into this by doing it in an automated way. So that might be through Terraform, because we're doing it through our CI/CD pipeline at deployment time, right? It might be programmatically directly with the API. And there's a whole ecosystem of integrations we have, like the Vault agent, as well as things like Kubernetes operators that allow you to integrate applications in a number of different ways. Our goal is to try and minimize the amount of modification to the app, and so to really integrate with the platform like Kubernetes, or to provide agents that can run as a sidecar like the Vault agent, or to integrate with your orchestration tool, whether it's Terraform or Ansible, So it makes it easy to integrate Vault with however the app is running. So really wherever the app is running on whatever cloud or platform on-prem, it's designed to be able to integrate. And then to really manage a broad set of the type of secrets, right? So really not just static values, but certificates, keys, databases, service accounts, all of those things we really want to be able to both manage and then automate the rotation of those things. And then make it simple to operate in a highly available, highly reliable way, whether that's self-managed or cloud delivered. That's really the goal when we talk about Vault. Obviously, this was really just high-level intro. There's a lot more detail in other videos and documentation, so I encourage you to check that out.